right, let me just organize myself so I still see that you guys are chatting at me. All right, so my goal here is to basically just give you an update on some of the new things on the Surge capabilities, things of that nature. I don't know why that just happened. It's weird. Okay, so there is a notebook that's linked to the webpage that Randy put up. We're going to be going through it in slide form, and there's some code and stuff like that. Some of this is not new to specifically to 5.7, but it's been new over the past about year or so. And we'll
Kyle, I think you're going to need to make the font a lot bigger for.
Oh no, I'm not going to present on this. It's going to
Okay.
be this.
All right. Thanks.
Yeah. Now this is just the notebook. This is the slides from the notebook. So hopefully this is big enough. Anyways, so the first thing I do want to say is there's been a lot of contributors to the Storm Surge code, and I want to thank all of them. They've been great because there's a lot of work to do and a lot of this, as you'll see, and it's somewhat tedious at times getting all this data to kind of behave itself. So thank you to all of those people, and I encourage everybody to contribute because I don't want to do all this by myself either. So thank you to them. So the big addition and kind of data mangling device that we use now is this thing called a storm object. It's a class definition in Python. It basically is capable of reading in and writing out various types of storm specifications. So here we're thinking of maybe a best track type of thing, so you know where the location of the eye of a storm is, the intensity, the central pressure, or maybe some other dimensions of the storm. These vary around the world, and they are occasionally updated. So we decided that instead of supporting each one of these different formatting types, that we were going to actually implement a class in Python rather than in Fortran to read all these things in, and then write out one format that GeoClaw can easily read in. So that's what the Storm class really does. You can use it for all sorts of different things, and I'll point out a few of those right now today. But the basic important point here is that it's just a data container for time series descriptions of a storm. Okay, so whatever that looks like, we're trying to read those all in and then write them back out. One of the big things it does handle are units. So a lot of these different formats have varying different units, and it tries to deal with those in a consistent way as well. Okay, so the core capabilities of this class is that it reads in lots of different storm formats. So ATCF, HERDAT, JMA. There's some that we have planned, and there are lots of different ones that people have contributed. We also want to be able to write them out. So note that there is a GeoClaw format that's to read into the code, but you can write out, change a JMA formatted file to an ATCF file. This class actually allows you to do that. You can also say modify all these storm datas and then write them back out. So you can actually create your own storms or modify storms from whatever you want and write them back out. And then there's just some things that are nice, like plotting storm track and intensity. If you have the packages, there's lots of categorizations. So if you want to see what your storm looks like in some certain categorization, you can do that as well. There's also some utilities. One of them that I use a lot is actually constructing the fields. So this would be constructing the pressure and wind fields from some parameterization model. So we have lots of different versions of these. In particular, there's, there's the Holland 1980 version of a parameterized storm. A newer one by Chavez, Lynn, and Emmanuel from 2015. There's an updated version of Greg Holland's Storm. There's all sorts of them. And I'll actually go into the code a little bit more and actually show you what those look like as well. But this does bring us to kind of our first demo. Oh, actually, I have one more thing. So the way we've actually changed this up, especially in the set run files, is that we try to download the Storm files from the examples directly from an archive online. This usually works. Sometimes those archives go down, which is unfortunate, but we hope not. We go on and fetch a best track file. This one is in particular for Ike, Hurricane Ike, which is in 2008. So here we're specifying what the parameterization reconstruction is going to be in GeoClaw itself. Ike.storm is going to be the name of the eventual file that we're going to use. We go out and fetch and unzip this storm file, which is an ATCF format. We read in the unzipped file, so now it actually just has to say, this is an ATCF file, I want to read it in, and it reads it into a bunch of different fields inside of GeoClaw, inside of the Storm object. Sometimes some of these data files actually do have events, like landfall. In this particular case, it doesn't have landfall, partially because it happened multiple times. So that is sometimes in these files as well, but we're going to specify a specific landfall, and we call that a time offset because you could think of doing multiple different time offsets. Landfall for a storm is just a really convenient one. And this just allows us to map basically the timing of the simulation to the timing inside of the storm file. Right? So you don't, since the storm files are usually done by date and hour in real time, the simulation doesn't care so much about it other than the fact that it has to map between those two things. And then finally, we just write this file out in the GeoClaw format so that the code itself can actually read these in. What does GeoClaw Storm format look like? It's fairly simple. It's not as arguably human readable, but it's very readable to Fortran. Basically, we have a header that says how many lines the forecast should be, that time offset, so again, 2008 in September. And then we have lines that represent, the columns are time, location, so those are the next two columns, the maximum wind speed, maximum wind radius, the pressure, and then the maximum storm radius. One of the nice things of the reason why we are doing this and having a new format is that we can add to this more columns if we get more fancy in terms of our parameterizations, which is planned. Because we control the storm format, we don't have to worry about adding things to this. So, and neither would you just have to rerun it. It would add those columns, even if you didn't have them. Unfortunately, the storm object doesn't contain rainfall. Now you could add a parameterization for rainfall. I know I've seen them. They're, a banded rainfall object would be nice. But we have not gotten to that point yet. That would be a really nice thing to discuss how we go about doing that. Just as an example of something that you could do, I just closed my window, so let's back up. Ooh, that was a little too big. Okay, so here we have some code. This is basically just a replicant of what was above. So here we are reading in the Ike data file. So this is just grabbing it. We are storing it in a scratch directory. That's, if you didn't know, GeoClaw often stores things in a scratch directory that stores topography, storm files, earthquake files, that type of thing. You can, in principle, you should always be able to remove everything in that directory as they should be downloaded. So we have all the things we had before. The addition here is actually the plotting code. This is a new feature that has just been incorporated into GeoClaw, and that's just to plot the storm track in intensity. So here you can see this is Hurricane Ike. This is just the default version of it. You can use Basemap or CartoPy to do this, or some of the other packages that do mapping. But you can see this is just simply colored by the intensity of the track as it goes along. So this is just a nice thing to look at. One thing I use this a lot for is actually doing ensembles. So if you have a bunch of storms, you can color their tracks and actually look at what some of the ensemble statistics really look like. Just switching but quickly back to the slides a little bit. One of the other big things that we did add were parameterized wind models, or more of them. We started with the Holland 1980 version of it. We now support Holland 2010, that CLE, the Chavez-Emanuel paper. We do have Slosh's wind and pressure field now. There's a very simplified Rankine vortex, a modified Rankine vortex, Maria and Willoughby. Some of these really do need more data than we generally have, so be cautioned by that. But we can, if you have the data, do a lot of these different things. These have been added to both Python and Fortran. The Python is in a pull request, so that's not quite ready, but it is all implemented in the Fortran code. So you can use any of these parameterizations, reconstructions, the wind and pressure fields that you would like. So what do these things look like? Well, I just pulled this from one of the Python pull requests. This is the Holland 1980 reconstruction. And basically what the idea is that you can reconstruct these in radially symmetric, in this case, cases. And the idea eventually is going to be that you can we'll create functions for you to evaluate this at any radius and angle to the eye of the storm, so you can do asymmetric things and plot them on mappings or whatever, so you can kind of check to see what's really going on. So again, just another nice utility for working with storm surge data and things of that nature. We've been working quite a bit on adding more examples. There is now a synthetic basin example. So if you're interested in trying to simplify and analyze various different things, for example, like barrier islands or things like that, you can kind of start with this new example. It does not, I think this is right now, and it's in lat long. If you want to go back to meters, that is possible. We have another example with that. I am in the midst of transforming the storm surge tutorial, not only to update it, but also to make it more complete. So you can see what it looks like at that URL there. It steps you through setup completely without knowing basically anything about GeoClaw, and kind of touches on all the basic things that you would need to do and specify for storm surge. We're going to also make this eventually a nice place to actually go into more depth if you're interested in those types of things. Like there's tons of settings for gauges and stuff that might be as useful, like Randy's demonstration of the Lagrangian things. So some of you may know that there are examples in the GeoClaw source repository itself, but there are also a lot of examples in another repository called apps. There are actually a lot of examples there for all of the ClawPack and GeoClaw packages. One in particular for Surge, which has been growing lately, is Surge examples. So there's a lot of different examples there, and these are meant to be kind of full-on validation studies to various degrees. So the data sometimes is a little hard to get, so usually you may have to actually contact the author. We tried to store those and make them downloadable, but that's not always possible. And I also want to say, again, this is a nice way to contribute. If you are doing your own storm, studying a particular storm, and you are willing to contribute back and just post it as an example, we're definitely interested in that type of thing. And we're working on a lot of different examples that way. The other thing that might be of interest, and this is coming from more of our research interests, and that's ensembles of storms. So trying to do risk analysis, trying to do maybe climate change types of analyses. These storms can be synthetic, or they can just be, historical storms. This is often just it's not hard to do this. It's just kind of annoying to manage. So we do have a bit of code that's actually been written specifically for storms management, either on a single workstation or on a large cluster, or even on a supercomputer, basically sending out the storms in order so that they can all be run in Slurm or any of the other queuing systems, things like that. So there is a tutorial incoming. This is a pretty complex piece of code, except it really isn't once you figure out what you need to do with it. So I highly encourage people who are trying to do this. I've seen about 10 different implementations of this now, and we might as well share what we have between all of us. So I'll try to post about the tutorial that is incoming on that. But if you want to take a look at it, the main piece of the code is on GitHub as well. And the storm specific version is called storm.py. So there's actually a version for that. And as usual, there's a bunch of bugs squashed. For instance, there was some bugs related to recording storm fields at gauges. One of the things you did want to do is actually record the wind speed and the pressure at gauges. Those weren't quite working. We figured out that there was kind of an order issue, but we fixed that, so that should all be working. Also, again, I just want to thank everybody who's contributed. Definitely, if you have questions about especially the storm surge stuff, the Google groups are still around. If you don't know about those, as Claw users and Claw Dev. We are going to start to try to use a Slack channel, and we're going to post a way to get invited to that shortly. And then there's, of course, GitHub. We look at that all the time. We're pretty, hopefully, quick to respond to issues. And things like that. And again, I just want to emphasize this is an open source community. Please contribute, especially if you have interesting things that you really want to get functionality out of, and you think it might be nice to have, or other people might want it as well. So that's kind of the update of stuff. I do have one more thing to show, but are there any questions before I get into that? If you have questions, feel free to put them up there. I'm going to show you some source code because, I feel like I have to.
Kyle, there is one question about, does the storm object contain rainfall?
Oh, yeah. So that was, I think I answered that to some degree before. It does not yet. That would be a great thing to add. There's a lot of interest in doing, obviously coastal coupling and flow into streams and rivers, since that has been more of an issue lately, especially with storms seemingly to stall over land. And we also think right now climate change might be increasing the amount of rainfall that certain storms will produce. So it does not yet, but it is definitely of interest. So if you have some ideas about that, please let us know. Okay, so this is actually the storm.py file. And I just want to point out, there's a lot of data in here that just, because every basin in the world, if you don't know already, calls things differently, different names for things. It gets complicated, and we've tried to actually allow or just code in various ways that we can simplify this down for everyone involved. So we have a few of these expanded names, especially just reading these files from various places. So ATCF, there's basins here. TC Vitals also has a set of basins. So this is where the storm is located. You also have different other things like designations, disturbance, tropical depression, tropical storm, typhoon, super typhoon, hurricane. There's all sorts of these things. And there's also events that we also try to kind of pick out. Yes. And then there's a lot of different readings in here. You can kind of see what different stuff we have in this. The kind of important point, though, is that we do have categorizations as well. So this is Beaufort, NHC. Clearly, we have more to do. But those are the type of things that we can add and actually do some of the kind of standard pieces to this. This is actually an example of how we convert units as well. And we also, anytime we actually do implement someone's paper, especially the parameterizations, we do cite them as much as possible. So you can kind of see here, we're citing a few of the papers that are the basis of the construction of the parameterizations. So if you want your parameterization in here, let me know and we'll put it on the list. These are only a few. We obviously have more in there. Someone asked to explain the storm ensembles and climate change a little bit more. The basic concept there is that we have the ability to, given a certain future climate, generate a bunch of synthetic storms. So Kerry Emanuel is well known for having the capability of doing this. At Columbia, we have a group that has another system for doing this. And basically the idea is that they're large ensembles trying to generate large numbers of years of data rather than relying on historical, although historical data you can use just as well. See, so in the idea is that you, in terms of the code, is that you have this ensemble of, say, ATCF version files or whatever it is, and you have the code that will actually manage creating directories of output, creating a bunch of run scripts based on a single set run, a set plot from GeoClaw in a make file, and it'll manage all the output, the plots, and anything else you want to have happen on multiple different systems. Again, Slurm, if you're using that from a cluster standpoint, or just a desktop machine. If you know how many cores you have, you can say, I want you to run 10 simulations at a time. I have 30 cores. Each one would hopefully use 3 cores. It's a little tricky to get to work sometimes, but it's stuff like that. So it really is trying to get at this idea that there's an uncertainty about a lot of this storm surge business. Same thing with tsunamis, really. And we're trying to run multiple storms to get a probability out like that. The storm surge code is parallelized, so is GeoClaw. It's parallelized with threading. So it's OpenMP. Generally, it depends on, for the storm surge, it can take hours to run, but it does depend on how much resolution you really need. So these can run from anywhere from 10 minutes to tens of hours. So that's one thing that's, it's hard to answer, but it is parallelized. One thing we haven't done is gone to massive parallelization. So things like MPI, and Donna, this is a great lead into what you're going to talk about next. But we've kind of stayed away from that, mainly, well, in terms of my interests, because I do have to run these gigantic ensembles. One storm simulation isn't going to cut it. We really do have a nicely parallelized problem to do. So we haven't really gone in that direction quite yet. Here's another question. Is that possible to use storm objects to test storm simulations in different sea level? That's actually one of the ensemble settings you can do. So if you had one storm you wanted to run for 10 different sea levels, you can totally do that. That's very easy to do. Another idea would be to use it for different tidal stages. So a similar type of idea. And you can multiply that across each of these. So this really is meant to be, a parameter sweeping type of thing, and you can do this all programmatically, so you don't have to do a lot of the heavy lifting. Anything that's going into the set run.py, and actually the set plots as well, can be modified. So that allows you to really get a lot of different things out of it, including the storm objects themselves. So you could say, I want this set of intensities and run an ensemble based on that, or I want these tracks to move up and down the coastline by certain distances. You could easily create that as well based off of one single storm. So we've done that type of stuff as well. Some of these synthetic types of things.